Hi everyone, how's it going? Today we're going to talk about cybernetics, and to do that I want you to go to Canvas. I want you to go to the module for this video if you aren't there already, and I want you to find the Loren Carpenter experiment from SIGGRAPH 91. I want you to watch that, and then we're going to talk about it. Alright, so Loren Carpenter and his experiment at SIGGRAPH 91. It's kind of incredible. It's this amazing moment in the history of technology where this idea of decentralized control becomes a reality. An audience spontaneously understanding and organizing how to play a game. It's the first instance of Twitch plays something. I'll link the full 11-hour Twitch plays Pokemon Red video in the module as well. But this idea, the self-organization that presents itself in any group of people, this kind of groupthink we sometimes refer to, isn't a new idea. It's not something that's first observed here at SIGGRAPH. It's something that we've known for as long as human history. And this generalizable idea that people think together and can organize themselves is something that the cyberneticists were fixated on. They actually began to think about how they could formalize this kind of working computationally. And they wanted to figure out a way to use this kind of anthropomorphic machine, this human-like machine, to actually create new forms of government, decentralized control, systems that would actually self-regulate and self-govern, systems that would actually change the way we live together. This was all embedded in a technological vision, intertwined with the advancement of modern computing. And so to understand this a little bit more, we have to dive into the history of cybernetics and what it actually is. And so starting first with the idea that the anthropomorphic machine obsession of humanity has not been a new thing. We can see it in examples such as Hephaestus from Greek mythology, the divine blacksmith who's crafting automatic machines. And we have obviously sci-fi examples. We can think of Frankenstein, a life brought forward by scientific advancement and electricity. We can think of Hal from 2001: A Space Odyssey, the superintelligence. You can think of modern movies such as Blade Runner or Her, which are both incredible AI narratives. But all of these fictional narratives speak to our fascination with our own likeness, our desire to personify machines as if they were made from our own flesh and blood. We have this innate desire to enhance ourselves with these machines as well, to see our own likeness in them and use that likeness to help ourselves. And sure, this is something that we're familiar in the modern day. This is AI's narrative now. This is the story that artificial intelligence tells us. But in the 40s, this was the cyberneticists' vision, and it wasn't a new one. So the vision of automatic machines presents itself in the later years of World War II, where automatic aiming machines and computational assistance was provided to pilots mainly, who were trying to solve hard problems like how to target erratic behavior in planes. How do we use control systems to actually extend the ability of gunners and things like turrets on planes? And it was this kind of first moment where we were solving this hard problem of the human-like movement of planes as they're controlled by their pilots, and how do we build computational systems that represent that control. It was in that moment that this vision had presented itself yet again, seeing our own likeness in the machine. Now, Norbert Werner, an American mathematician in the 1940s working at MIT, began to think about this as something that was a generalizable principle, something that we could extract from nature and actually formalize mathematically, conceptually. And he called this theory, this general theory of machine control, he called it cybernetics, and defined it as, in 1948, he defined it as the scientific study of control and communication in the animal and the machine. It's as broad as that, as wide-reaching as that. Control and communication in the animal and the machine. And cybernetics was a framework that allowed inventors, technologists, to actually begin to interpret and endow their machines with new anthropomorphic ideas. And Ashby was one of these cyberneticists, Ross Ashby. Ross Ashby was inspired by the Sperry turret and that automatic control system. He was inspired by the control systems that Werner was pioneering. The idea of working on an artificial mind, how to represent that, most complex of human features, the mind, how to computationally represent that, was his fascination. And he began working on regulatory systems, and he was using the rhythms of the body as inspiration. And one of the features of our body is that it's homeostatic. It actually can self-regulate towards an internal temperature. We have a consistent body temperature, and our body is able to act based on different kinds of input to change the way it behaves in order to regulate itself towards an equilibrium, that homeostasis. So I'm talking about sweating. We sweat to cool ourselves down and maintain a homeostatic temperature. That kind of biological system that he saw out there in the world, much like what was shown in Loren Carpenter's experiment at SIGGRAPH in 91, was the thing, the fascination that he had with the world. So he wasn't alone in this vision, and many people flocked to it in the post-World War period, where technology had begun to advance exponentially quickly. It was a moment where human-machine collaboration had been extraordinarily successful at both ensuring the safety of the future in the West, but also inspiring generations of people and giving them a vision giving them hope that technology could be their savior, that technology was their savior in the form of war machines. But the cyberneticists, with their obsession with this kind of natural phenomenon and the advancements in technology from World War II, came together to bring about Ashbys Homeostat, a system that was actually able to represent this kind of automatic regulatory system, the system that we have inside our own bodies that regulates our temperature. And it wasn't some kind of biological system. This was, an analog computer, one that was able to regulate itself when it became destabilized. It would always return to an equilibrium. Now, this is a kind of simple, early technology. It's just the seed, the kernel of an idea that's carried forward into a much more complex digital age. And it wasn't to a small fanfare that these ideas were received. In fact, this vision of self-controlled systems, machines that had human-like features, was reported in the New York Times in 1949. And there's this quote which is really amazing because it resonates so strongly now. These machines are not science fiction dreams. They or their components already exist. In a special appendix, Dr. Werner discusses a more speculative possibility of building an electronic chess player, something that we've done, something that AI in the modern day has successfully achieved. He goes on to say, whether chess and automation is ever built, the future of electric brains with radar and photoelectric cells for eyes, sensitive microphones for ears, and other man-made sense organs. These machines will do a great deal of the work that human brains are doing now. They may replace many persons trained to answer questions involving only routines of detailed, repetitive thinking. What does this sound like? We have this exact same conversation today. This is the automation of jobs that AI threatens. In 1949, they were having the same conversation. And so this is this great historical moment where we have this kind of techno-futurism, this optimism about the way that technology will change society. And we see it repeat itself time and time again. It's happening 50, 60 years ago. It's happening now. As designers, we need to use these historical examples to reflect on and account for the way that technology moves and how we can actually design for the future. How does reflecting on the historical example of cyberneticists, in this case, people who thought that they could use decentralized systems of control, feedback systems to actually change the way we govern ourselves, and their failure, how do we use that to actually inform modern day design? Well, I think it kind of comes together in the example of Sophia. Sophia, the video is on Canvas, so go and check that out now and pause, come back. But Sophia is an artificially intelligent robot, one that's based on modern neural networks. And the neural network itself is obviously, in the name, it is a model of the way the brain works, where a neuron works. And Sophia was given citizenship to Saudi Arabia. And you can see the response of Sophia in that video. It seems kind of bizarre, this notion that this robot is being given citizenship. It presents the kind of just the facade that is this techno-optimism. This robot is so clearly and distinctly robot-like, and the features of humanness that are endowed upon it are actually kind of complex, like they're not clear. I don't think any one of us would say that they think that that robot is not a robot or is, in fact, the same as a human. And confusing the categories of human and robot just opens up so many questions. And us as designers, we have to think and grapple with that. If a robot can be granted citizenship to a nation state, then what does that mean for the way that we think about designing for artificial intelligence? It's an open-ended question, and it's something that we have to begin to grapple with. So the cyberneticists' strange experiments with feedback and control systems that could self-regulate, systems that we see bring about experiments such as Loren Carpenter's experiment at SIGGRAPH, are fascinating, and they actually show that history is set to repeat itself. We're here at the precipice of a new growth in AI again, and we continually tell ourselves and speak to ourselves about the way that technology will yet again solve the next generation of problems, and it may well do so. But it's important for us to reflect on the fact that there is many failed narratives in the history of technology. And when we're designing a generative system in this class, and we're thinking about generativity in general, and systems that have an embeddedness of agency and control in them, it's a design feature that we're actually looking at. We're actually trying to think about the way that the system controls information. How does the system actually augment and interact with its environment? And these are high-minded concepts, but they're important because they attach themselves so necessarily and easily to the way that we think about designing for the future. And so this is yet again meant to be a conversation. This is a way of opening up a dialogue about what we think the future should be like. Do we see these kinds of biological reflections in digital technologies? Or do technologies instead shape the way that we behave? Or is it a bit of both? These are the kinds of questions that are embedded in simple generative systems, ones that play with where autonomy is, how much control the system has, and how much control the human has. And so I encourage you to engage with some of the readings for this week and start to think about these questions and endow your generative designs with a vision for how automation and control can actually be a way of thinking about organization of information, but organization of people. All right. Good luck. See you soon.